All right, so I want to do a couple examples of proof by contradiction. The first one, was essentially from the textbook. I'll change the numbers around just so it's slightly different. But the statement was if something like this: if 7n plus 4 is even, then n is even. So first thing I'll do is flip that around as the contrapositive. So I'm going to say assume n is odd. And so if I assume n is odd, then I can write n as 2k plus 1 for some k that's an integer. Then I can substitute that right here. And I would say that means that 7, just a second here. All right, sorry about that. I'm substituting in the n value, 2k plus 1 plus 4. And then that gives me, I guess, 14k plus 7 plus 4. So I can make that 14k plus 11. Remember, what's my goal here? I assumed that the second part of it was odd, so I negated the second part of it. So my goal is to prove that that negates the first part. So I'm going to try to prove that what I just got becomes odd. And so that equals 2 times 7k plus 5 plus 1 extra, and that is odd. And so by contradiction, I prove the original statement. Now, you can also prove it just directly. So this is proving the original statement directly. You could just say 7n plus 4 is equal to, I'll use just a different letter, 2p. And then I'm going to try from there to prove that n has to be even. So what I'm going to do is get n by itself. So 7n is 2p minus 4. And then a lot of people were tempted to divide by 7, but then you really don't know much about n. So you can't really conclude that n is an even number. So the nice trick here is to get n by itself by subtracting 6n. So now you know that n equals 2p minus 4 minus 6, which minus 6n, excuse me, which is 2 times p minus 2 times 3n, and that's even. So you go boop, 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 and you proved it directly. So sometimes contradiction is necessary to prove things. Other times it's just an alternate tool that you can use. So whenever you're looking at a statement, get used to flipping it around in your head and seeing if one direction is easier than the other direction. Okay. The classic proof that I showed you in class that I'll just show you again here is that the square root of 2 is irrational. You should be able to do it with other square roots. So let's just try square root of 3, see if I can get through this here. So we're going to try to prove that square root of 3 is irrational. So step 1 is to assume not, i.e. that square root of 3 equals p over q. P and q are integers, and I'm just going to say that it's in simplest form, no common factors. Okay, so then what I could do is square both sides. So then I get 3 is p squared over q squared, and then that means that 3q squared is equal to p squared, and this implies that p needs to equal 3 times k for some k in the integers. That's the only way that you can get a multiple of 3 on the left side, is if there is a multiple of 3 on the right side. And so if we write that out, substitute this in for the p-value right there, then we get 3q squared equals 3k squared. You can see how this is very similar to the square root of 2 that we did in class. Like that. Divide both sides by 3, and you get q squared equals 3k squared, which implies that q is equal to 3t for some t in the integers, and that's the contradiction. So we know that the original p over q must not have been in simplest form. What I want you to think about is, if I go back through this proof and change the 3's to 4's, where does it break down? Because we know the square root of 4 is irrational. So let's go through it. 4, 4, 4. And here at 4q squared equals p squared, I can't necessarily conclude that p equals 4k, because it's possible that p equals 2k. Because right there, we know that 2 times 2 is equal to 4. Some of you might protest, well, that requires you to know that there was some number that multiplied to make 4. Yeah, that's true. That is a fair criticism. But you can here prove that it is possible to write the number 4 in terms of p over q with no common factors, where the p value is equal to 2 and the q value is equal to 1. And then when you look at this step right here, there's no longer any contradiction. The p and the q work. And so it's a little bit weird. At first, it was weird for me to think that, okay, the breakdown with the square root of 4 requires you to know that 2 times 2 is equal to 4. And that might feel a little weird at first, but there is no such number that works for 3. There is no such number that works for the square root of 2 or the square root of 5 or anything else like that. So yeah, it does require you to know a little bit of arithmetic about natural numbers in order to prove that the number is irrational, which is maybe not so surprising, because irrational numbers sort of are built after an understanding of natural numbers. So anyway, thanks for watching. Please comment, ask questions if there's anything else I can do to help.